Thanks for coming, everyone. I'm going to take a slightly different approach to this presentation than ones we've given in the past. We've focused a lot on wearable and flexible hybrid electronics. Today I'm going to talk a little bit more about semiconductor level packaging applications and how they apply to the world that we live in the printed electronics space. Our focus has been kind of along parallel paths at SunRay, where we're working on both materials for semiconductor packaging as well as the flexible hybrid electronics world. And I think everybody would here agree that those two worlds are starting to collide more, and that's really the basis of the work that we did here. So we're going to talk about our anisotropic conductive epoxy. For those of you who aren't familiar with the technology, I'll give you a little background on how it works. We're going to talk a little bit about the technical attributes, the properties, and the processing of the material, and then I'm going to get into some of the advanced packaging solutions and how they translate into the printed electronics world. We'll go through a couple of case studies and talk about some of the potential applications and some of the current applications we're working on. And if we have time, we can cover a few questions. So our anisotropic conductive epoxy technology is designed to be an alternative for bonding down onto either problematic materials because of the substrate bond capability, because of the temperature limitations, the flexibility of the material, or perhaps the processing that's required to get a good adhesive bond and make component attached down to that material, including very fine pitch. So if you're familiar with the typical ACA or ECF materials that are used, those are processed in a way that require both heat and pressure through way of a thermode, which is usually a singulated process. We can capture the same performance with a Z-axis interconnect that doesn't require pressure, can be processed at very high volumes at high speeds, and provides a superior bond to that material at a lower resistance interface, more so than anything other than a low temp solder material. And you're seeing here an example. So basically we're taking a random dispersion of ferromagnetic particles that through a proprietary process we've developed, we can coat them with a number of noble metal finishes. Normally it's going to be silver or gold. Those particles are then dispersed into a two-part polymer epoxy matrix, which is 100% solids material. And that is functionalized by way of our ZMag pallet. And that pallet is a permanent magnet. It's not an electromagnet. It's a rare earth technology specifically designed by us for functionalizing the column formation of our material. And it's designed to be plugged into standard SMT line processing. So no special equipment, no extraordinary CapEx required. It's simply taking a carrier pallet, placing it on top of our ZMag pallet, and then going through the typical processing, whether it's going to be a box oven, a reflow oven process, or even a hot plate in a lab environment. We make a number of versions of these technologies, primarily based on the coarseness of the particles, which then controls the kind of pitch that we can manage. Our coarse formulation can go down to 200 microns in pitch, and when I talk about pitch, I'm referring to center of pad to center of pad. Our fine material can go down to 100 microns in pitch, and we're in the final stages of developing our ultra-fine material, where right now, and I'll show a slide subsequent to this, that shows we're getting very high performance and high yield down to 60 microns, working on evolving that by a combination of formulation technology and process to get to 20 microns in pitch. And that's really where you're talking about really high-level packaging and semiconductor applications. So these particles are formed. They can be processed at a range of temperatures. These are not sintered materials, so we can operate and cure these materials as low as 80 degrees C, and we can go up to about 160, 170 degrees C. I talked about not requiring any pressure. So this is a very strong structural bond, very low resistance interconnection. Typically our bond at the bond line at the interconnect, the resistance is going to be from 7 milliohms centimeter all the way up to 20 milliohms. That's driven by a combination of which formulation we're using based on the particle size distribution as well as the bond line distance for the component between the component and the conductive pad. We don't use solder bumps. We don't need solder bumps. We're not reflowing like you typically would in a solderable application. We want to go direct to pad. We can work with a flip chip or a reverse die. We don't underfill because the technology is its own underfill. And as a result of this, normally because of the bond strength, there's no actual completed encapsulation required once the material is used for bonding. So this gives you a little kind of schematic of how the process works and what we're doing. So we're looking at a typical SMT line, You're printing down the circuitry. Once the circuitry's been printed, you're going into the application of the ZTACH material. It's